Welcome back to class 12. Here's an example to go along with that introduction. Very similar, pretty much to what was what was narrated, but here's we're going to do this with numbers. So we have two rigid insulated tanks that are connected by a pipe and a valve. One of the tanks has 0.5 kilograms of air at 200 kilopascals, 300 degrees Kelvin, and the other is 0.75 kilograms of air at 100 kilopascals and 400 degrees Kelvin. The valve is open and the air comes to a single uniform state without any heat transfer. How do you determine the final temperature and pressure? All right, so not out of the realm of possibilities of something that you might want to try to calculate. It's a practical problem. It's not necessary to draw the system, but it helps me to think my way through a problem, so I would suggest that you do it too. I don't know why B was to the left and A was to the right. I'm going to switch things up. A and B. I like it that better that way. So we're using air in both of these. So, and see the mass of A at state 1, right there, in that place, it's going to be 0.5 kilograms. And the mass of B is 0.75 kilograms. The pressure at A is 200 kPa, and the pressure at B is 100 kPa, so pretty much atmospheric. And this is 2 times atmospheric pressure. TA1 is 400 degrees Kelvin, and TB1 is 300 degrees Kelvin. Other things I'm probably going to want to need to know. Let's just go as we go along. All right, so conservation of mass would be M2. It's going to be equal to MA1 plus MB1, or 0.5 plus 0.75. And we're going to get 1.25 kilograms. We need to find, if we want to find the specific volume, what we could do is we could use ideal gas law, right? Ideal gas law of PV equals RT. So you have V is equal to RT over P. So we need to get R, and this is air. So we go to table, I think it's A5, and R for air is 0.287 kilojoules per kilogram. So now we can get the specific volume for both of these, and then from that we get what the total volume is going to be. So far, we're just guessing at what we're going to need to do. We haven't really done any aha moments about how we're going to go about it. That was kind of in the previous video. We kind of led us to the spot right here. But let's just try to see what we can get. It kind of makes sense that we want to know the specific volume. We're given all this other information. So let's try to find VA1. That's going to be R over TA1 over PA1, or let's just for the first time through go and use the units. So the R is 0.2. Well, I like to make it to Newton meters per kilogram. 287 Newton meters per kilogram times my T1, which is 400, A1, 400 kilo. That should have been kilogram. Yes, Kelvin, degree Kelvin. I forgot that Kelvin in there. And this is going to be, I'm going to turn this into newtons per meter square meter. And so it's going to be 200,000 newtons per meter squared. And you can see the meter, no, the meter doesn't go away. We want meters. We're going to have meters. Meters are going to stay in there. But the newton's going to go away. Kilograms going to stay there, and the Kelvin's going to disappear. And so we're going to come up with a cubic meters per kilogram, and that's what we want. And so we're going to get 0.4305 if I did it correctly, which we don't know for sure if I did or not. And then VB1, likewise RTB1 over PB1. We just go 287. We can actually probably just make it 0.287 then without doing that thing anymore. But I'm just going to go ahead and keep up with what I've been doing so far. And so it's 100,000. And so what we're left with is, where'd you go? 1.148. So with this now, and we also know the mass, we could find out what the volume of each of these is going to be. And that's going to be good for us because then we're going to know when we're done what the specific volume is of the whole thing, because we can find, we're going to have the total volume and we're going to have the total mass, so we can get what the total specific volume is going to be. And it has to be true. And all we did was use the conservation of mass kind of that and the ideal gas law thus far. So let's see, if we go right over VA, and that's not VA1 because it's going to be, it's always going to be the same volume. It's going to be, let me think of that here. My mind isn't working. I have to multiply, right? VA1 times MA1, right? And so we're going to get 0.4305, and you can check with the units here, cubic meters per kilogram, and we're going to multiply by 0.5 kilogram. So yeah, that can't, so that's definitely going to give us a volume. Good news. 0.2153 cubic meters. VB, all the same thing, just with different numbers, right? And so this needs to be that. And the mass needs to be 0.75. And what we're going to end up with for the volume, 0.8610 cubic meters. Now there's like a kind of a weird sort of thing that happens right here, the coincidence. I don't think it's just a numerical coincidence, but just be on the lookout for it. It really puzzled me, and I hope it's not a math mistake I made, but you'll see here in a second. We're going to go V total is going to be equal to VA plus VB, or 0.2153 plus 0.8610, and that's going to be equal to, is this right, 1.076 cubic meters. All right, so we can find what our end result is going to be. So that's going to be little v2, which is just going to be V total over mass total, M tot. So, or M2. I guess that's what I called it up above, up here, M2. Try to be consistent. Now here's where it's going to get a little weird, and I just think it just happens to work. The numbers just happen to work out that way, but it bothered me. 1.25, and so we end up getting 0.8610 cubic meters per kilogram. And you'll notice that those are the same numbers right there, but it has no connection to it. It's just a coincidence. Might be some mathematical reason for why that just happened. I'm not quite sure what it was. Okay, so this is convenient for us because we can attempt to look up what the, using this, did we do that? I'm trying to think. I think it's probably just one of the things we want to get. No, we can find the, we're going to use this for the final pressure. So first thing though, let me look up. We going to use, so that was the we were using the almost everything here except for the ideal gas law was all about the conservation of mass. Let's look at the conservation of energy. All right, so we had U2 minus U1 is equal to Q1 to 2 minus work 1 to 2, right? So there's the energy equation, but we're going to say that it's insulated and it's a constant volume process. So all we're going to left with is U2 is going to be equal to, basically equal to U1, right? U2 is equal to U1, which means it's also going to be equal to U1A plus U1B. So we know we're going to get M times U2 is going to be equal to, so it's M2, M1A times U1A plus M1B times U1B. We could approach this in two separate ways. One is that we could, and the book wasn't, I think I'm going to go ahead and use tables for these U's as opposed to using specific heats, but we could use the specific heat. Notably with the specific heat, we would be canceling out, it would appear in all of these, and we would cancel them out. So I can do it in both ways, but I haven't actually written it out. That's why I've written out what's in the book. So let's look up, assume the pressure doesn't matter for air, and let's look up in the air tables that are in the book, the internal energy, right? And hopefully they're the same for this version as the one that I got this problem. No, this should be the same version. It should say, yeah, it should be the same. All right. So let's see here. Let's go to the tables. Go to table A something or other. I think it's A7. There you go. Ideal gas. Air for properties of air. And we have 300 degrees for one of them, right? And 400 degrees. So here we go. We're going to use this number and this number and put them in there. So I'll write that down. Say table A.1.7. We got U1A. And I wrote underneath there is the, is that right? No, this is 400 degrees, 400 degrees. And did I write it correctly? No, I probably didn't. What if I got it wrong? Let's see, let me write it down while I'm looking at it. So the 1A, or A1, whatever you want to call it, is 400. So that's a 301.04. I wonder if I messed this up. I bet I did. Well, we'll redo the numbers then. And then we also had B1, 1B at 300 degrees at 214.36 kilojoules per kilogram. All right. So what we should end up finding, and I'm not writing it out like they did in the book. I usually just leave it into the thing. I guess we could write it over that way. I just end up calculating it that way anyway. I'm going to get my mass of 1.25. Our total mass was, where do you go? At the top. 1.25. The U, we don't know, U2. It's going to be equal to this mass. Let's see, I'm going to try to get this right. 0.5. And that's going to be times this one. See, I think I got these swapped. It's easy to make mistakes when you're not really paying attention. 214.36. It's interesting. That's a small number, the big number. That's a big number, the small number. Okay. So the U2 we're predicting here Remember, this is conservation of energy right here. This right here. This was conservation of mass up here. Conservation of energy in a most basic form, but it's the basic form, no basic basic example. That's what I want to say. $1.255. Yes, I did it wrong. So 249.03. These are kilojoules per kilogram. Now I can look that up too. Unfortunately, I will now have to do a interpolation, unless it perfectly worked out somehow, and it did not. But it's somewhere between 340 and 360. Almost directly in between the two of them right here. So I'll see. I'll write this out for my interpolation. I'll go bring this over here because it makes for a pretty boring video to watch me do this thing. But, you know, what we're trying to do is we're trying to solve for the final temperature, right? The final temperature of the thing. And then with that final temperature, we get the final temperature, spoiler alert, we can use this specific volume to, well, actually, tell you the truth, I think we could do it without it. We just need that temperature, and then we can get the pressure, because it's a constant volume process. Yes, that's true. Okay. So I'll take it back. No take backs? Sure, take back. All right, so I'll write out my, here's what we have to do. We're going to 340. 360, and we had, what we just found was 249.03, and up above we had 243.11. This was 257.33, and here's the T that we want to find. So 243.11 minus 249.03. Watch previous videos if you want some more interpolation explanation, or I could do it right now. Why not? All I did was subtract this one from that one and divide it by this one from that one, and I'm going to set it equal to this subtracted from this. Excuse me. This subtract from this, and then this subtract from this. Yeah, okay. As long as they're the same pattern, you will come out with the same thing. I almost messed it up. So T, it's not terribly fun to do, but it's not really painful, I don't think. All right, so this right here is like 41.6%. We're going to multiply it by basically negative 20. All right, and then we can subtract 340 from negative. There, boom. And we end up with negative 348. Yeah, negative 348. But this is negative, so it can be positive 348.33 degrees Kelvin. And now you could also just go ahead and write PV over T is equal to, oh no, you couldn't do that. I'm sorry, silly man. That's why you can't do it, because it isn't just that. We could find this, right? That you could find P is going to be equal to RT2. We just got T2 over V2, right? And so that's going to be 0.287, and that's 348.33, and it's divided by, did I get that right? Yes, up here somewhere. right there, 0.8610. So P is going to be, let's see, get rid of that, 287 times 0.8610. Boom. Ooh, dang it, right? 0.287. Let me just do it the right way. 287. Okay. 348.33 times 0.8610. Got it. All right. So that comes out to 116.1 kPa. Some reflection on this. I might go a little bit further, even though the video is already overly long at 20 minutes. This is like maybe a bet that you would have with a friend. Let's say a friend who's also an engineer who had this tank. You know, we have these two tanks put together at different insulated temperatures. They say, okay, what do you think is going to be the result if I open this valve? And then you can argue back and forth. Well, let's do it out by paper and then do it for real and see who's correct. All right. So it's like a real experiment that you could try. And you need to think of it in those terms, right? That this is like a real thing, and you could actually measure those and try to see how close you came. Tell you the truth, I have a strong feeling that you wouldn't get exactly this. You know, from all kinds of various things, details that might be going on. Kind of funny. For whatever reason, I think my wife is playing Duolingo, and my watch is telling me that. Don't you think that's interesting? We could have also, by the way, when we got to this step right here, we might have been able to use specific heats. I don't like doing that because I think specific heats should usually be used not to find actual values, but instead to use to find differences. When you have differences in temperatures, I think it might be a bad habit to think of in those two terms. But we can look up the specific heat of air. Right? It's it's like right here in a table nearby. So I just want to try it and see. I don't know if I'm correct or not, if that would give me the values that I want. But here you go. So we should be using this specific heat for constant volume one when it comes to internal energy. We should be using the pressure one when it comes to enthalpy, but we are dealing with internal energy in this calculation. So I still didn't write it down because I can't remember things. 0.717. But I don't think it matters, 0.717, because we're just going to take this equation right here. Where'd you go? Focus, yeah. This guy. And write MCV T2 is equal to M, so this is M2, is MA1 CV T1A, or A1, I don't know, I'm not getting them right. Sorry, so MB1 CV T1B. You notice that the CVs all cancel out. I don't quite like that, but it's true here. I just want to see what my T2 would be. Just curious. T2. It's going to be MA1 over M2 T1A plus MB1 B2 T1B. And these have to be, you know, we've got to make sure that they're in Kelvin. But we get mass of 1 was 0.5 and 1.25, and this T1 was 400 plus This was 0.75 over 1.25, and this was 300. Now those tables are more correct than using the constant specific heats, because this constant specific heat is just an assumption. But let's see what would happen. All right, and then 0.75 or 1.25 divided 300 times, add them together. We get 340 degrees Kelvin. All right, so it's a little bit of an estimation right there, but we're kind of in the ballpark. And then, of course, we would use the ideal gas law to get the pressure. I think the tables are probably a better way to go, but we will often do the assumption of a constant specific heat.